all what we did in the last class. But I think I'm not going to. So of course, we consider always separable Hilbert spaces. Then it's a metric space, even metric space contained in complex numbers. Star homomorphism, star homomorphism of C of X on some B of H. Maybe it is fine, but we write it n equal to 1. Maybe it's fine. Okay. Doesn't matter. Or you can indexing set where indexing set is countable. Yes. Each measure mu n, you have a pi b of L2 of mu n. Okay, you have L2 of mu n and L2 of mu n, pi mu n of f acts as multiplication operator. Then you take the direct sum of L2 of mu n. Okay, there. So this is an operator acting on that. Okay. Pi is unitarily equivalent to pi mu n. This direct sum u unitary. Sum of n equal to 1. Okay. And any element of L2 mu n is direct sum of vectors. Okay. So that's how it's going to be. It's a family such that norm of Fn squared, summation norm of Fn squared less than it. That is that's the definition of this. This multiple. So this is how it acts. And such so that that's a theorem. So want to make this statement. First, you want to say that this B of H can be expressed as direct sum of cyclic representation. Okay. So you can take any vector, and I mean that is proved by Zorn's lemma. So you take the collection of Hilbert spaces Hn and with cyclic Hilbert spaces Hn. Okay, such that Hn and the family is, I mean, you take this kind of Hn. This is the cyclic vector. And H family. Inclusion partial or another. Family has, because if it is if space invariant, it will leave the orthogonal complement also invariant. So you will get another some other one. Technical representation. Take just a definition. The orthogonal complement also invariant. But we have maximal family. The maximal family and theory. This orthogonal complement as well. In given a measure, you have a representation pi mu. Okay, that pi mu can be extended to the representation of the L infinity, okay, just by the same multiplication, and that extension is unique. Okay, but for abstract representation, you get the unitary. If you have any cyclic, you get each unit, each n. Now you take the direct sum of unitaries. I mean, you can. This is like GGG. It's not scalar. It is pi different operator. Bucket, right? So it's like G in the diagonal. So like from uh, so percentage pi mu n given by the any measure you can define a representation. You take the cycle. I mean, how do you when you have a representation, cyclic representation, use that like this. So that, and so it's a problem. Since I is a unit vector, it's a problem. So, Now choose. This is just right. Information and equal to 3%. And mu of E so is equal to any set of the this is clear. It's clear. But we want to prove the following. And further, P ln mu E then of course the condition is satisfied, and norm of phi in ln mu become collection of measures. You produce a single measure using that, and it satisfies the supremum of these norms. Then Fn something. Again, now, three for nominal infinity. In some instance, they will be same. Usually, it's not. Yes. So norm Fn that this here the z and so on. In this case, mu A converges here in mu n pi mu. I have to say pi mu of f. Okay. This pi, this pi is essentially a multiplication representation on different components up to unitary. You take the same unitary, this pi mu n. I mean, each pi mu n can be extended to pi mu n tilde. Okay, and you take, so you have a direct sum of pi mu n tilde. Bring that back by the unitary. Okay? I mean, we do, usually it's not written; it's understood, but that is how we define. Where if pi mu tilde equal to 2, not pi mu. I mean, you have a representation pi. It here. So I should have, let me erase those and bring it. This is a special theory, but I have a theory. unique. If you take pi tilde, there is no there exists a pi tilde. There exists a measure also. There exists a measure. You know. Yeah. So the mu is already there. We have got the mu. We have got the mu. There's no need to talk about that. The measure exists. Okay. So there exists. Yep. There exists a pi tilde. Unique. There exists a unique pi tilde. It's the same method. So this direct. Okay. From L infinity. Using that pi, we got a family of measures, and from the family of measures, we got a single measure. Okay, and this L infinity x mu is the bounded anyway. It's a bounded, essentially bounded. So this is currently contained inside. Here, that B of H. What now true? That's the I mean, K and in L infinity mu and supremum over K norm F in K L then infinity. Okay. So for F K, we have mu n for all n. In L infinity mu and also L infinity mu, that is in L infinity mu and also we have proved that. I mean, that's part of the we have to. And pi delta, yes, it's not reference to this is a pi delta. Okay, converges strongly to pi delta. This is strong convergence. That's all. Okay, proof. But first we want to prove. We have to prove that. So let phi is the I want to make some digression. So here I will do it in this board. So this is about general matter theory. I'm not sure whether it was class. We have any function in the infinity mu for some measure. How is this norm infinity mu equal to infimum of all those m such that mu of this mod f greater than m is 0, right? This is how the L infinity norm is defined. Okay. So I first want to show that this infimum is actually a minimum. Infimum is infimum, which is defined through epsilon and other thing. Minimum is something when the infimum is attained. That's what the minimum is. Okay. So, okay. Now this is f infinity. Yeah? Now it's clear that so this implies there exists Mn greater than 0. Of course, M is greater than 0. Mn greater than 0 such that Mn decreases to norm f in infinity. Okay, mu. That's when just norm f, it's L infinity now. Okay, so that's what, of course, is an infimum. So there exists Mn which decreases to that, such that mu of mod f greater than M is equal to 0. Now these are all increasing set. Right? As n goes to infinity, Mn goes to this, decreases. So these are all the increasing sets. Okay, so this set increases to, this set, norm f greater than Mn. This set increases to norm f greater than norm f infinity. Okay, norm f infinity. Okay. So then mu of this will increase to this. So these are all zero, so this should be also be zero. So this implies this infimum is attained. Infinity is equal to, this implies mu of norm f greater than norm f infinity equal to zero. This in particular says that norm f infinity. So if you take the set f is equal to some e is equal to mod f greater than, this is the function greater than norm f infinity, norm L infinity. Okay. This is the set. Okay. The norm f infinity is supremum of all those t such that mod of f of t in, supremum of mod of f of t is in E complement. It's clear, of course, in this set, when it is in E complement, it is less than or equal to norm f infinity, and the supremum has to attain. If it is not attained, then that will not be the infimum, you can argue, right? Okay, right? The supremum has to be this. If you take the supremum of ft in this set, you get the norm f infinity. When I say f infinity, it is sorry, L infinity, it's not there. So the L infinity norm is actually a supremum over some set, where you remove a set of measures. Okay, so this is the statement I want. Okay. So, okay. Direct, so now, so let f is equal to this set greater than. Now, f in phi of supremum of phi is the term of phi in mu is the supremum of L infinity. There mu is that. So now this is equal to such that norm of phi L infinity equal to supremum of complement. Now define n equal to f union the set D derivative absolutely continuous with respect to mu. That's what we have noticed. Okay, mu is equal to 0 if mu and e equal to 0. T derivative is a function. It's a matter. Wherever that function, that's what I mean. If this notation is okay, we are comfortable with it. Wherever d mu equal to take the random t and f, then we call it as f. But we have 0, f is this set. Because the definition of L infinity of f is 0. Even of f is also 0. Now, this, n of fn equals 0. Mu1 of this set is 0, mu1 of this is 0. Now, intersection of fn. Okay. And this is in fn, of course. F intersection of fn is less than equal to 0. This does not depend. So this implies mu of intersection of fn equals 0. This is true of n. of intersection of the currents are zero. So in this, we can actually remove a set of measure 0 and take the supreme. That's okay. Okay. I mean, if you take the, you can take the supreme by removing a measure set of measure 0. Okay. So that's what the definition is. That's okay, no? So norm of f infinity of L infinity is equal to, this is a set of measure 0 and it contains f. Okay. Is equal to supremum. Can remove a bigger set. Okay. Not, I mean, this f is there. Apart from f, you can take a bigger set. Supremum of t, supremum of p of t, mod p of t, where t is in x minus that union of, intersection of n equal to 1. This is okay. Okay. Now this is equal to, of course, supremum of mod p of t. Union of x minus each one, right? The complement. And that is equal to supremum over n, supremum. I mean, it's just supremum. Okay. Can t is in x minus. Okay. You remove the fn, f is here, f is contained in that. You remove a bigger set, and it is just the supremum. Okay. There is a small, I think there is no explanation given in the book. I thought it was okay earlier, but I think this is not clear. They say that it is equal to, this is just, there is no reason, I don't see any reason that this is equal to norm of mu n. Okay. So this book, this says that this is equal to norm of supremum of L infinity mu n. I don't see that. I can only see that this is greater than or equal to that. Okay. So we have phi of L infinity is greater than this. Okay. I think we have to prove this is actually equal to that by the following. Suppose P, I mean, that means suppose the supremum is strictly less than that. That means supremum of L infinity mu n is strictly less than some m, which is strictly less than or equal to some m, where this is less than or equal to phi of L infinity mu. Okay. Suppose this is the case. I mean, I should say that the supremum is equal to that. If not, then this is there exists m like this. Okay. Suppose this is true. This just implies, from here it follows. This just implies mu n of, okay, phi, mod phi, greater than that m, equals 0 for all n. Right? That's the definition of this. This is less than or equal to this. That means this, right? This is the infimum of all such m. So this is true. Okay. So this implies mu, this, but this is true for all n. So this implies norm of phi greater than m equals 0. This contradicts the fact that m is, I mean, p infinity, L infinity mu is strictly greater than m. Okay. So because of that, it follows. I don't see why I can have a counter example where this is not equal to this. This is only strictly greater than this. By this argument, it's okay. So all these things imply norm phi L infinity mu is equal to the supremum over n norm phi L infinity mu. So this is done. Okay. Now we want to prove the strong convergence. And is it clear to you that this T going to UT U star, this map preserves the norm? Is it clear to you? You can, that's because it preserves the inner product. For any U, this is equal to less than or equal. Now you can use U is unitary, U star is also unitary. And any unitary takes the unit ball, it's a bijection between the unit ball. So remove this. So, this T going to UT star, they have this is equal to this. The actual isomorphism, isometric isomorphism. There is no other nicer isomorphism than this. T going to UT U star. Okay? This is the best isomorphism. There are isomorphism which doesn't look like this, but between some P of K, these are the only isomorphism. I mean, you can prove it. Okay. So any isomorphism between these two, which are between H to K. Okay. I mean, you can say orthonormal basis will be taken. Or, I mean, you can work with rank 1 operators. There is something called partial matrix units. If you have isometry, then you can talk about this kind of, I mean, where these things are taken, you can say, then you get the unitary and you can write. Okay, this is a good exercise. You can try for finite dimensional, then you can imitate it for infinite dimensional. I forgot to say, this pi tilde matrix. See, you have a pi, but when you have pi, something we should. There's nothing about the, it's contractive. Okay. This pi mu n, okay, this will be isometric. This will also be not isometric and CF. But this is isometric on L infinity. Okay. That's what we have proved. We proved it's isometric on L infinity. Because L infinity norm is smaller than C of x norm. Of course, if they are equal, then this is isometric. Okay. So this pi mu n tilde, sorry, pi mu n tilde norm of F, this is to norm of F, L infinity. This is what we proved. Okay. When we discuss, first time when we discuss this representation, this is what we proved. This is isomorphic. Okay. So here all this pi mu n tilde, that's isomorphic. You want to prove that this pi is also isometric. That it's a unit. This pi is isometric. There's nothing about pi, which is, okay. I mean, even though we don't have a statement about pi, pi tilde is isometric. Huh? Representation. It's an extension of pi. Pi tilde means pi. This is pi. You already proved the uniqueness of pi mu n tilde. Pi mu n tilde is multiplication representation. Pi mu n is also a multiplication. But pi mu n tilde is a unique extension of pi mu n. Of course, an extension is pi. But that is a unique representation extension satisfying this condition. The first statement, pi tilde. Pi mu n tilde. Direct sum, you forget the unitary. Everything is a nice step, then and so That is your pi tilde. Okay. Pi tilde norm is just the diagonal operator, right? Pi tilde f is just the diagonal sum of pi mu. I'll write it. This is equal to the assignment equal to supreme of pi. If you have a direct sum of operators, I mean, if something like a diagonal operator, infinite diagonal operator, then the norm is supreme of those norm of the diagonals, diagonal elements. Okay. So because this is proved, we have proved that pi tilde given is isometric earlier, right? We have proved pi tilde given is isometric. So this is supreme over this. This is exactly pi tilde. So this pi tilde is isometric. That the uniqueness is clear because each of them tilde, I mean, pi is decomposed using pi mu n. Pi, you have the representation pi, which you started with. That is decomposed with pi mu n. Each those pi mu n can be uniquely extended to pi mu n tilde under this condition. Okay, so this is the unique extension. There is no 1, 2, 3. It's okay. Here, what are the one thing? Place 2. So that's clear, no? Some functions convergence in measure mu, then it converges in mu n, right? Because mu n times since it plus 1. So you want to prove some, yeah. Estimate mu of this set fk mu of whole set. I mean, there is nothing bigger than that whole set. These are all positive measures, of course. So this is the mu and n. Okay. Then delta. This is less than It is this one. The whole thing less than delta. This is 3. So we have uniformly bounded. Yeah. You have a collection of Fk. Mu is less than infinity, so mu should also be less. That is what. Okay. Of the area theorem. Okay. So all the direction of elements converges. Okay. So we proved about strong convergence theorem. So primo. Okay. Okay. And this is of course, I mean, Ln, I mean, this is equal to that, and that is equal to normal infinity mu n. K for all k. That's what. Okay. So this direction element is well defined, and the norm of that is exactly. Yes, you have defined it for all k. So this k is an operator which are uniformly bounded. Yes, and a total set. See, you see this point. Hn. Okay. You have operator k is the direction of something, some t and k. This t n for a fixed n, t is the direction of that pi of f mu n. Okay. Nk converges to this place. This just for k. L2 mu k mu n. Converges. This Hilbert space is span closure of all those direction, finitely many direction elements. What is this direction of? You take element, you take finite direction, or you take infinite direction. You take finite direction and take the span, and you take the closure. Okay? So if this Tk converges to P and P converges L2 mu n. Okay. With PK converges, I mean, only if you write it, you will really get convinced. But I want to say, yeah. Keep forgetting it. Okay, that is what 2 says. Phi tilde of mu n, we have already phi mu n. What does it mean? That, like one by one. The mu n again. To infinity of mu n. Right? The Hilbert space is direct sum of L2 mu n. So direct sum of n. So direct mu n fk n equal sum of z. There otherwise 0. Okay. It's a finite each layer. So when you act on UNFK, equal to 1 to of layer, right? Finitely many of them non-zero. Okay, that is a total set in a direction of L2 mu of xi n elements like this with xi n equal to 0. Finitely. Okay. This is the total set contained in direct sum of L2 mu n is total. Okay. So this happens on a total set, and these operators are uniformly bounded in K. Okay, that's for L infinity. Okay. Direct sum of phi mu n f k. Okay, supreme. Okay. Proved a proposition that if you have a sequence of operators which converges pointwise on a total set and it is uniformly bounded, then it actually strongly converges. So from that, it follows that the sum of A will converges to mu f k. The pointwise convergence happens on a total set, and the operators, this is only for sequence, of course. This will not work for net. And the operators are uniformly bounded, then convergence is strong. I mean, it will pointwise convergence happens on. So it's done. Now 3 implies 2. We have already proved 2 implies 2. So phi delta, I mean, it's actually equal to phi delta, okay? It happens for, I mean, if anything happens, T, U T is can, U is an isomorphism. This point-based convergence, I mean, U is, have two Hilbert space H and K, we have a unitary between them. To every element, you have a some element here. If point-based convergence happen here, that same thing will happen. Okay? So unitary, you don't have to worry about the UT. I mean, you don't have to worry about the unitary. So direction pi mu n. So it will happen over pi tilde. Unitarily defined by the unitary. U, this operator U star. It will happen for that. 3 implies 2. So suppose Fn K converge on each coordinate it will converge. Up to unit pi delta of Fk delta pi delta F. This is pi delta. Not actually as I said, pi delta is defined by the unitary. Pi delta and direct sum of this are defined by the unitary. Okay. The operator strongly small operators are only also converge small. But we have already equivalent to the convergence measure. We have already proved. What we proved is multiplication representation. That's what we proved, right? Okay. So this implies Fk converges to F in mu n. So if you see and if you have any doubt or anything, I can go to some argument. All we have done is we had a representation pi of C of x, okay, that we decomposed into direct sum of pi mu n. Each pi mu n we extended to pi mu n delta. We didn't direct, we have a representation pi that is unitarily equivalent to some direct sum of representation pi mu n. Each pi mu n we extended to pi mu n delta. With the same unitary, by bringing back by the same unitary, we define pi delta. And all this statement we proved about that pi delta. Okay. We only used this measure theoretic idea. And everything else followed by what we have done already. We have proved the isometry, no? Yeah. Did we prove the isometry? Did I forget? Proved that. So, isometry part also we have proved. Now, I recall the earlier theorem which we proved. Now, this is the spectral theorem. For self-adjoint operators. Okay. E in B of H, self-adjoint. Then, this is not spectral theorem, but it will go from this. You will do for a normal operator. Okay. Now, I will state that this is what is called functional calculus. Okay. What I am proving is what is called functional calculus, and which we will prove for normal using normal operator. We will prove the direct integral part of it. Once we want to prove the same functional calculus theorem for normal operator using what we proved here in this, what is proved in this theorem for self-adjoint operator. Okay. So T is a self-adjoint operator. Then there exists a unique isometric isomorphism. Star by isomorphism, I always mean star isomorphism between pi, between. So, and x is equal to sigma of t. The spectrum of t. You have a self-adjoint operator. X is a, usually x is an operator, but here I am calling it as a. So x is equal to sigma of t. Since it is self-adjoint, this is contained in real line. Okay. This is contained in real line. So pi is from C of x to C star algebra generated by t and 1. Okay. C star algebra generated by t, which is called C star algebra generated by t if you want, which is, we want a unital C star algebra, so I am using 1. So if you have a t, unital, if you have a C star algebra t and 1, this is just, you take all in T. Since C is T self-adjoint, you take complex polynomials in T, okay, and then close it. Okay? Then take the closure. Because if you take product of polynomials, you are going to get polynomials. So that's an algebra. You just close it. Okay. So you know already what is this isomorphism, such that phi of this f naught, where f naught of t equal to t, is one variable polynomial, f naught is equal to t, and pi of course it's unital, so pi of 1 is 1. We've already proved this. Okay. You take pi of f naught equal to t, then pi of any polynomial p is equal to p of t. You can take polynomials in t. Okay, that will preserve the norm. You remember that theorem what we have proved? I mean, this is what we first proved. Okay, you have self-adjoint operator, then you define from C of x to here, you define pi of any polynomial. You have polynomials here which are dense here. Okay, complex polynomials, okay, which are dense here. Of course, p is there, p bar is also there. You don't have to worry. So pi of p equal to p of t. I mean, you insert the t in the polynomial, the variable, you just insert the t. Okay, this is norm-preserving, which follows from, which is norm-preserving for the self-adjoint operator. Not in general, for normal operator, we can do it. Okay, that is because the spectral radius formula. We use the spectral radius formula. We use this, no? Norm of p of t. By definition, this is equal to spectral radius, supremum of lambda in p of sigma of p of t. Okay, and this is equal to supremum of lambda sigma of p of t is p of sigma t. Spectral mapping theorem, p of sigma t. We proved this. Okay, this is by spectral radius formula for normal operator. Spectral radius formula is something 1 by n, p of t power n 1 by n, the limit of that. That is the spectral radius for general spectral radius formula. For normal operator, these two are equal. Okay, and by spectral mapping theorem, p of sigma of t is equal to sigma of p of t. Because of that, this supremum is equal to this. Now, this is just equal to the infinity norm of the polynomial. I mean, the C of x norm. Okay, the continuous norm, C of x, uniform norm of this p. So this p going to p of t is norm-preserving. So it will extend to, I mean, it's a norm-preserving map between, I mean, it's a isometry. So in particular, it's uniformly continuous. So you can extend it. And that will continue to be a homomorphism. Okay, we went through all this. Okay. So we have a map. This is already proved. This pi, so you can define, I mean, okay, I will define it later. So you have a pi like this. Okay. So we have proved. Now from that theorem, we have the second part. There exists a measure mu on this x, x is equal to sigma of t. You have a measure on the spectrum, okay, mu on this, such that, and a unique pi tilde from L infinity mu, L infinity x mu, okay, into, I mean, actually, this will land up in what is called, the range will be what is called the von Neumann algebra generated by T. Since we will see that later. Okay. So this is just, we just write it into B of H. Okay. There you have an isomorphism between the system algebra generated by T and C of X. Here it will also be an isomorphism between L infinity x mu and the, what is called the von Neumann algebra generated by T. So we will come to that later. For the time being, this is just a representation. L infinity P of x, such that pi tilde of this f naught is again equal to t. Okay, that's the only condition. And that I'm bored to write that strong convergence. That is, if you have fn and then L infinity mu and supremum fn less than infinity, and fn converges to f in mu, implies pi tilde of fn converges to pi tilde of f strongly. Okay, or whatever that statement. This is all clear. Huh? This is what we have approved for any representation. You have some representation, you have a pi tilde from that all these things follow. I mean, this is proved, already proved. And from earlier, I mean, from the earlier theorem, previous theorem, what we have proved, this follows. Okay? There is nothing to prove. Okay? Is what is called the functional calculus. You can, I mean, if you have a t, you can, okay. Now you can define f of t by this. Phi of t. Phi of f is an operator. You call that operator f of t. Singular mu. That mu is associated with pi. It comes from the pi by whatever we have done. Okay. It's in L infinity mu. Right. Define phi of t is equal to that pi tilde of. Pi tilde of t is an operator. You call that operator as phi of t. Okay. There's no, I mean, this is just a function of an operator. If you have an operator, you have the square of the operator, which is defined algebraically. Okay. For example, square root, how you define? If you have a positive operator, you can define a square root. But to define that, you have to go through something. But by this functional calculus, it is easy. I mean, it will do all that. I mean, it's very easy. If you have a continuous function, when the continuous function makes sense, of course, square root as a continuous function should make sense only for some function. No? So like that, sine, cos, log, everything you can define of an operator. In fact, if you have a measurable function, we can talk about function of the t. So this is what is called. We did this if you have a Banach algebra element, if you have an analytic function, define around the spectrum, neighborhood around the spectrum. You have a neighborhood where the spectrum of that operator is contained. If you have a Banach algebra element, x, and suppose the sigma of x, the spectrum of that x, which is defined for any Banach algebra element, is contained in some neighborhood, and you have an analytic function on that neighborhood, then you can talk about analytic function of that Banach algebra element, which is again a Banach, which we saw. Okay, using the power series expansion, we can define. So here, if you have just a continuous function, you can define. If you have a measurable function, you can define. The continuous functional calculus directly comes from that. But using all this measurable, I mean, representation theory, we get the measurable functional calculus also. Why we want to do measurable functional calculus? All we want to do is whatever the characteristic function, indicator function, and then define this. Okay, and this will satisfy. This is a function, idempotent function, right? Idempotent. This is, if you call this function phi or something, phi square equal to phi bar. So this will be a projection. A projection is something which satisfies this, right? And this function, phi, I mean, we will discuss all this later. I'm just saying why we want measurable function calculus rather than continuous functional calculus is you have to get this projection. Once we have this projection, then t going to t will give you a measure, spectral measure. Using that spectral measure, we want to integrate and get that operator back. I mean, from the using the spectrum and the spectral measure, we will be able to expect, I mean, operate. Okay? So that is, you know. Before that spectral theorem, this is the I mean, the basic ingredient is this functional calculus. Okay? So we have a continuous functional calculus and measurable. Finally, I want to prove this mu, whatever is occurring, that is unique. I want to prove that. L infinity mu. If you have different L infinity, we should not have different L. See, this mu is this infinity is something. Right? It has not L2, LP, everything depends on mu. Okay? But L infinity is something which depends on the zero sets of mu. It's not something it has nothing to do with that. But the same, the L infinity is same. Okay. We have used L infinity as function space. I mean, that's how we have been using it, but they are all equivalence classes, right? These are all equivalence classes, but we freely, I mean, abusing notation, we are using it as, you should assume that comes from, we are using an element from the two the same sequence. And what does it mean? That just means they are mutually absolutely continuous. Okay. Oh, no. Something equal to some measure, mu of e equal to we said the representation is direct is a measure and the representation is unique. That's what we prove. Now here we are saying that the previous theorem. Once okay. Let E some set contained in, I mean, E is a sigma or whatever. It is a X, whatever we have. They're considering throughout, okay, some metric space. Contain already proved that C of X, continuous functions are, I mean, you said you have seen, it uses the regularity. Continuous functions are dense in L infinity, not, no, L2, right? L2. Okay? L2 was not in, continuous functions are not dense in L infinity. They are only in L2. Okay? L infinity is something much bigger. Okay? In fact, L infinity, C of X is separable, L infinity is not separable. Okay? So, yeah, okay. That's that. L2 convergence will imply it, I mean, you have to you have continuous function, or we have proved it, we went through Lucin's theorem and other thing. You can use that also. Okay? Fn converges to 1V. Okay? Then and I mean, you assume that they are uniformly bounded also. You can explicitly get a continuous function using the regularity property. Okay? I mean, if you take the value between 0 to 1. Okay? Now, I mean, f is a function which takes value 0 in one set. I mean, it's using that Urizon property, Urizon lemma property. Okay, So that is how the Fn is defined. Okay. Okay. I mean, if you have a set E contained in B of X, you can approximate inside by compact set, outside by open set. Okay. That complement is again a closed set, and you have a compact set inside. Now these two are disjoint. Okay, such that the difference between the difference measure is epsilon, less than epsilon. Now you take a function which takes 1 in the inside set, inside closed set, outside that open set, it takes the value 0. That will exactly, okay, that will approximate this. Okay, so you have a function like that. Okay, now so this simply converges to strongly by tilde of 1. I mean, sorry, you take this in. We have a representation and we got, suppose we get two measures, mu1 and mu2. Okay, you define a measure mu equal to, okay, this mu. This then now I mean converges to F in mu. Okay. By the okay. Pi oh, 1 mu1 of 1 strongly. That also pi converges of 1. Okay. Pi of continuous. Fn's are continuous. Pi both are extension. So that is equal to pi of Fn. Okay. So this is the same sequence. So this is equal to pi mu2 of 1 mu. This implies pi mu1 of 1 equal to 0, pi mu2 equal to 0. But pi mu equal to 0 is exactly equal to saying that measure p is 0. Zero. Pi of e equal to 0. This representation is isometric. Ln of some 0 of the set is 0. Okay. So L infinity norm same as the operator norm because this pi mu theta is an isometric. Okay. This operator norm of this is equal to L infinity norm of 1. If that is, if this is equal, if the 0 function in the L infinity. Okay. Even though it's not a 0 function, as a function in L infinity is a 0 function. Pi, this is equal to 0. On the other hand, this will imply the other one is also 0. That will imply this 1e is a 0 function because this isometric. So mu2 of e is also 0. It's clear, no? Okay. It follows from this property. Okay. Property. They can take continuous, but they can't continuous function because it's this is implies measures extending that are mutually absolutely continuous. That implies that the L infinity is same. There is no difference. Okay? Function, sequence of continuous function. That's what. That is why I do. There is no other reason. Okay. So you have Fn, which are continuous function, which converges to the one E. Then the converges strongly. To continuous function, they are same. Okay. So they have the same. But they are same means they are same from the mutual reciprocity continuous. Okay. And they are same, the elements need not be same. But zero will coincide. I mean, the measure need not be same, but the zero sets will coincide. This is the isometric. I mean, measure. So, about normal operators.